Hello. So today we will start from anisotropic etching. So in the last class we have talked about isotropic etching, where in all the directions the material was etched with the same rate, right? And now we will see that where the directionality or the crystal arrangement of silicon will have an effect in its etching. So in that case we will use actually KOH. Like KOH is a very popular anisotropic agent. So mostly used, one of the mostly used etchant is 30% KOH at 70 to 80 degree centigrade. Another etchant is EDP at 115 degree centigrade, and then we have also tetramethyl ammonium hydroxide, which is also called TMH, and at 70 to 90 degree centigrade. So we can use all these three chemicals for etching silicon, but there are other chemicals also which you can use, but these are mostly used. Actually KOH and TMH are the most popular one for silicon anisotropic etching. Silicon etching here these etchants are dependent on the direction. Okay. So what happens is, along the 100 or 110 or 111 the etching rate is not same. So typical values of relative etching rate is given here, as you can see that 111 is to 100 is to 110 is 1 is to 400 is to 600, and that difference is pretty huge. So as we know from our crystal structure itself that in the 110 direction one atom is connected with the bulk with only one bond, right. So this is like more probable case, like, or the most probable case where the atom can easily get removed from the surface. So in that case the etching rate is highest, like 600, whereas 100 it is medium, like 400, and for 111 case one atom is connected to the bulk with 3 different bonds. So it is the most stable plane, and in that case it is only 1. So it means that if I etch it, let us say for 1 hour, if I get 1 nanometer for 111 plane, for 100 and 110 we will get 400 nanometer and 600 nanometer of etching. But what we need to remember here, that though the etching rate is pretty small, but still the 111 plane also get etched, it is not 0. As I am saying that anisotropic etching, what does it mean? That you can see from this picture. There you can see that, so this surface is 100 surface, means it is normal at the 100 direction. As it starts etching, then this plane, let us say if I want to draw the surface here, then this surface also will be 100 surfaces, right, and these surfaces also will have higher etching rate, but before that itself 111 plane comes. And from our previous slides we have seen that the 111 plane makes an angle of 54.74 degree almost with the 100 plane. So in that case this angle is 54 degree angle, and in this 111 plane the etchant will move very slowly, because once the 111 plane is open, then the etching rate in this direction goes very slowly, right. Etching rate in this direction goes very slowly. So that is why this surface opens up, and how much is the depth, accordingly you can form this kind of U shape or like V shape pattern, where the bottom edges, both the edges can merge also depending on the opening. Like here it will merge at a longer distance, like here it will merge at a longer distance, right. So it, after going even more in that silicon bulk, then it will merge both the surfaces, but here it has merged even much before that, because the opening is pretty small. And this region here are the masking layer, which will not get etched by the KOH etching. And if we see after etching, if we see it in the under the microscope, then it will look something like this, where this is corresponding to, this image is corresponding to this opening, which is the cross sectional view, and this region will be the flat region where where we can easily see the light reflected. From the top surface also light gets reflected easily, but these black regions are these slopes, right. These black regions are these slopes where the light is not reflected, so it is like this. So from the bottom the light is easily reflected, but from this region light gets reflected to some other place. So this looks black. Okay, I will show the real picture in the next slide. And then, so in this case you can see the bottom bottom side of the sample, which is open and which has a lesser in dimension from the top opening, whereas here you will see only the line, because all the 111 planes have merged. From all the sides the 111 planes have merged, so you will see only this kind of straight line. And point to be noted here that you see that the length of the line is also small, right. It is not the complete length. Complete length is this much, but here the length of the line is small, because here also we have 111 planes open, because like from this opening it is coming as 111 plane, and these two sides also it will go as 111 plane. And here now we can see the photograph, real photograph of the etched surface, right. There you can see that this is the top surface, this is the bottom surface, and this is the top surface, which both are reflective, because the light is coming from the directly gets reflected from the bottom surface as well as the top surface. But the slopes are black. These black regions are the slope where from the light comes here and then reflected in some other direction. So this looks black, right. And here and the dimension of the bottom surface is also much lesser than the opening, that also we can see. And this dimension actually can be calculated from the geometry from this image. So that we will come to, we will discuss later. Now this graph is showing that how 100 plane of the silicon etching rate in 100 plane changes with KOH concentration. So as we can see here, according to this graph, that for lower concentration we have a very high etching rate, right. For lesser concentration we have a very high etching rate. It does not change much for till certain concentration, but after that it drops down very fast, right. So below 20% concentration surface becomes actually very rough, and insoluble precipitation also are formed. So if it is below 20%, then the etching rate is very high, it is very aggressive etching, and in that case because of aggressive etching the surface also becomes very rough, right. So the RMS roughness, or the if we calculate the roughness of the film, will be very high, and in that case some reaction product will be there which will like precipitate, because those are insoluble in the solution. So how KOH etching exactly works? So H2O has a high dielectric constant about 80, and it polarizes KOH, and it becomes K plus and OH minus ions, like it ionizes into its cation and anion. Now silicon is oxidized by reacting with this OH minus ions, right. If KOH concentration is increased, the fraction of OH minus is inhibited and the reaction rate falls, because as we have a very smaller concentration, more number of ions we will get, whereas if we add more and more KOH, then the ions will be lesser, like the K plus and OH minus ions will be lesser. So in that case the reaction rate will fall. Now we can add isopropyl alcohol or IPA, that also reduce OH minus formation, and hence the H rate reduces. This is due to the lower dielectric constant of the IPA. And another important point is that H rate goes up with increase in KOH temperature. So if we increase the temperature of the solution, then the etching rate also increases. So the important point to note here is this concentration is one kind of control which we can select, and accordingly can choose how much etching rate we want. Then adding IP is another kind of control which we can add and in specific concentration, and then we can control the etching rate. Temperature is also another control knob or another handle for that. And why we need to control the etch rate? Because in some kind of application we will need very small etching, very small amount of etching, let us say 2 nanometer, 3 nanometer etching, or let us say 10 nanometer etching, and very fine etching, like the surface should be very small, surface should be very smooth. So in that case we can use very slow etching rate so that the surface will be smooth. Or in some cases where we need, like we need to etch probably 1 micron or 1000 nanometer, right, and in that case initially for let us say for first 900 nanometer we can go with very high etching rate, keeping the concentration higher. So in that case surface will be etched very like very fast, and it will be a little bit of rough, but after that the later on we can use even higher etching rate, or you can use IPA to reduce the etching rate, and accordingly we can generate smooth surfaces. So the final surface will be much smoother, and also we can finish the process faster. Now in this graph we are showing different effect of different parameters like temperature, concentration, and different planes, etc., and IPA also on KOH etching. So in this case, all the cases, if we see, the first case is 100 plane with 20% of KOH, right, and 250 ml of 20% of KOH and 250 ml of IPA, and this is how with temperature the etching rate changes. And this, you see, this is the this is plotted with 1 by T. So with temperature the etching rate actually, with increasing temperature the etching rate actually increases, because in this direction 1 by T is increasing, that means T is decreasing. So as we are decreasing the temperature, etching rate falls, right. Now 100 plane with 20% KOH and 250 ml of IPA has the lowest possible etching rate. Then 110 plane with the same KOH concentration, so then we can see that 110 plane have the higher etching rate than 100 plane, right, with the same KOH concentration and same amount of IPA. Next case is where we have the same 100 plane and same percentage of KOH, but we are not adding any IPA. So as we discussed earlier that adding IPA reduces the OH minus ions in the solution. So now we have more number of OH minus ions in the solution. So this will oxidize the silicon even faster. So the etching rate is even higher. So etching rate is not only higher than 100 plane for that condition, it is also higher than now 110 plane which was etched using IPA. And if we now use the same condition for the 110 plane, like the same 20% KOH without IPA, then 110 plane also have now the highest possible etching rate. It is higher than all the other cases. So there you can see that KOH concentration is already a parameter what we discussed in the previous slide, but the IPA as well as the temperature and the directionality or the which direction we are etching, then all of these are different parameters for controlling etching rate. Now in that case, actually one thing to I would like to mention, that is IPA we can select that whether we would like to add or not, temperature we can decide, but usually the substrate we are bound by the design, right. What kind of, if the design or my device needs 100 plane, then we have to use 100 plane. If it is 111 plane, then we need to use 111 plane, because there are different parameters which will also depend on this crystallinity. So that is not on our hand much, but we can select different kind of temperature and KOH percentage to control the etching rate. So what are the different reactions, what actually happens while silicon is etched by KOH? First of all, the OH minus ions oxidizes the silicon and it forms this silicon hydride element. Now simultaneously water is reduced also, like OH minus and H plus is also there, so what is reduced, leading to evolution of H2. the complex silicon further actually reacts with hydroxyl to form a soluble silicon complex, which is silicon dioxide with 2 OH minus ions, right. So, this is the final product with easily dissolves in the solution, and so the silicon gets etched. So, this is the final reaction, a silicon plus hydroxyl ions which are coming from the KOH and water, you will get this dissolvable reaction product, and with that hydrogen. From silicon we move to silicon dioxide etch rate with KOH, and silicon dioxide etching rate with KOH is also very much important, because most of the cases we have, first of all, silicon has always some native oxide layer on top, which is silicon dioxide, because it gets exposed to the moisture, and then the dangling bonds easily reacts with the water, and it forms kind of a native oxide layer. This silicon dioxide also is used as the masking layer. So, in the previous one of the slides, like this slide, we have shown this masking layer, right. So, which will not allow the silicon to get etched below it, right, and this can be actually silicon dioxide. So, we can put silicon dioxide on in some according to our design. So, how we can do that using lithography, that we will discuss in some other class, but the point is here that silicon dioxide can act as an oxide as an etch top or the protective layer or the masking layer. As I was saying that even though the masking layer for the masking layer or the protective layer, the etching rate is small, but still there is some amount of etching. So, like here you can see that the silicon dioxide have a etching rate of like below 70 or to 80 nanometer for different KOH concentration, and for different KOH concentration the etching rate varies, but it is below 70 to 80 nanometer. Now, if we go back and see it for KOH for silicon, then we see that the etching rate here is given in terms of microns per hour. It is, you can see that this is like 40 or 50 microns per hour, whereas for SiO2 or silicon dioxide it is 60-70 nanometer per hour. So, the etching rate for SiO2 is almost 1000 times smaller than the silicon, and this is a very important point, because we can use silicon dioxide as a protective layer, and let us say if we are etching for 1 micron, in that period, in that time 1 micron of silicon, let us say we need to etch it for 10 minutes for 1 micron of silicon etching, then in that 10 minutes SiO2 will get etched only like 5-6 nanometer, right, only 5-6 nanometer of SiO2 will get etched in that 10 minute. So, that much of oxide layer is good enough to protect the silicon layer, because SiO2 layer will protect the silicon layer until it by itself it gets etched by the KOH, right. So, if we deposit a like 100 nanometer thick silicon dioxide layer, so let us go back to this picture again. So, this is let us say silicon dioxide, and I am etching about 1 micron of silicon, and for that let us say we need 10 minutes of time. Then in that case this silicon dioxide can be of let us say 50 nanometer or 100 nanometer also, because in that 1 hour this will get etched only by 5-6 nanometer. So, this thickness also will get reduced. Let us say this will come to some place, like this, right, little bit lesser the thickness of what it started with, but ultimately it will still protect this region, so the silicon will not get etched, right. So, SiO2 has a small much smaller, almost 1000 times smaller etching rate under KOH etching compared to silicon. Now, the next way to control the etching is boron doping. In case of boron doping, what happens is, initially let us say if it is 10 to the power 18 like 10 to the power 18 atoms per centimeter cube, then in that case we have the usual etching rate of KOH, like without doping or with doping it does not matter much. But as we increase the doping rate like 10 to the power 19 to 10 to the power 20, then the etching rate drops down drastically. You can see here that this is normalized with respect to the maximum etching rate, and there it stays at 1 for till certain doping concentration, but after that it drops down drastically. So we can also just dope boron in certain region to reduce the etching rate in those regions. So then in that case that will act as a masking layer. And now we will see that how we can use this KOH etching for creating different geometries, and we will use the etch top layer also for creating this kind of geometries. So let us assume that this is a silicon wafer, like half of the silicon wafer, you can see this half circle, right, and there we have 3 different opening. Here we have a small opening, then we have a little bigger opening, and then again we have a small opening, right, even smaller than this the first opening. Now in this case, the first case, if we the cross sectional view is drawn in the bottom figure here. You can see this is the cross sectional view of the same geometries here. This is this red side is the etching, like the masking layer, and we have etched the KOH, we have etched the silicon from this direction, from the bottom, right, from the bottom, and then this is the hole opening and this is the bottom hole. So let me just write down here. So this is, let us say if it is 100 plane, then this is the angle which is 54.7 degree. Okay, 54.7 degree. All of these angles are 54.7 degrees. Of these angles are 54.7 degrees. Now with this angle here, the silicon wafer thickness is such that I will get a through hole. So this is completely, so light can pass from the top to bottom, right, this is a through hole. Then in the next case the hole size is even bigger, the opening is even bigger, so there also I should get a through hole. But what we have done in the other side or the opposite side, where we are etching from the bottom side, right, and on the opposite side or the top side we have doped boron in this region. So as we have doped boron, the etching rate in this region becomes the smallest. So the KOH will not be able to etch this region of silicon. This region of silicon will not be etched by KOH etching. So this becomes like a thin membrane. This becomes like a thin membrane. So if we have, let us say 500 micron thick of silicon wafer, and then this region can be like 50 or 100 nanometer, which is boron doping has happened, and or even little higher, let us say 100 or 200 nanometer. So in that region we get a very thin, like 500 micron nanometer or 1 micron thick membrane, which will not get etched. Whereas this is the smallest opening hole, so here both the sides meet much before it can reach the bottom side of the plate. So this through hole, this membrane and this V-shape hole all are made using the same KOH etching by just using a etch top layer here and different kind of hole opening. And these different geometries like membrane, through holes, or even this V-shape wall have different applications, which some of which we will see in the next module. But this like one kind of application for the membrane is, this is very much useful for pressure sensors. So we can connect a pressure port here, can connect a pressure port here like this, and then if the air pressure is applied here, then this pressure will build up and that will make the membrane to bend like this, and then we can measure the deflection of the membrane by some characterization technique, by like optical or electrical, and can measure that how much is the deflection and also how much is the pressure of the pressure of the chamber which I want to measure. So that these things we will discuss in the next module. So this is another application. So we have seen in the module 1 that we have used cantilevers for different kind of sensors, right. Now how you can make a cantilever? We can make the cantilever such that the only in using the cantilever geometry, this region, this violet color region or pink color region is only boron doped. So this region will not get etched, but all the sides will get etched. Now all the sides as it gets etched, cantilever with is not much. So the material or the liquid can go below it. So like this is the cantilever, let us say this is the cantilever, and then this is only doped with boron. So this will not get etched, but all the sides are open. Now from this side the liquid can like sink in and can etch the bottom side of the silicon, of the bottom of the cantilever, which is like the normal silicon, because the boron doping only will be in top few nanometers, like few hundred nanometers or such like that. So it will not go at the bulk, right, it will not go in the bulk. So that bulk silicon can get easily etched. So ultimately we will have, let us say these regions, the other regions are also boron dope, so this will also not get etched, but from bottom of the cantilever the material will get etched. So now this will be like a free cantilever, this will be, so now this will be like a free cantilever. It can easily bend because it has a vacancy or empty space below it, so it can easily bend, and this kind of device we can use for different kind of sensors. Thank you.